Everyone, and today we're going to be exploring an infinite geometric series. So in this video, I will give you a brief definition of what an infinite geometric series is, as well as some examples that we can do to further improve our understanding. So let's get started. So many of you may have heard what a geometric series is, and that really can be displayed in this form. So if I have a sum that goes from n equals 0 all the way to infinity, then my geometric series can be displayed in the form of a times my common ratio of r to the power of n. And what does that really mean? Well, a is always going to be my first term. So if I start off with n equals 0, and you can even test it out. If I start off with n equals 0 as a times r of 0, well, we know this gets canceled out to 1. So a is naturally going to be that first term. So that's how we know that a is our first term of our geometric series. And the r to the power of n, well, that r is going to be our common ratio. And what does that really mean? Well, each term we have, we are going to multiply it by r to get the next term. So let's go ahead and expand this out to see what it really comes down to. So if I have a, that's going to be my first term, and then add it to a times the r. Because if I sub in n equals 1, that's what I get, the a times that r. And then it goes on and on and on. So plus a times the r squared as my n equals 2, that's n equals 1, n equals 0. And as you can see the pattern, I'm really just subbing in my different value of n to get that next term. And each time we can see we're multiplying by that r. So I have r here, r squared. Next term will be, as you probably can guess, r cubed, because again I'm multiplying by that r. And since our series goes on to infinity, since that upper bound is infinity, well, guess what? It's a times r to that n, because n can be anything from 0 to infinity. So that's how we know this is our geometric series. And again, r is that common ratio, and a, if I didn't clearly write that out, a is our first term. So our first term of this series. And we do have some rules for these geometric series. Specifically, if our common ratio is going to be less than the absolute value of our common ratio. So whatever we're multiplying each term by, the absolute value of that, if that is less than 1 and greater than 0, well, then our series is going to converge. And what does that mean? Well, that series is just going to approach a finite value, because as we multiply it by a number between 0 to 1, and notice how these are non-inclusive. There's no equal signs here. Because we multiply by that specific value, it's just going to get closer and closer to 0 each time, or a finite value, and it's eventually going to converge. So approaching a finite value, that's what it really means. Converge means approach some finite number. That can be 0, 1, 2, 3, so on. And later we're going to see that there is a specific formula for finding that sum. Even if it's an infinite geometric series, we can actually use a formula to find the sum of that, which is actually pretty cool. Now, if you say that it converges, well, there's got to be some condition saying that it diverges, right? So our infinite series, if that ratio is greater than or equal to 1, notice how I have an equal sign here, that's going to diverge. And what does diverging mean? Well, that means the series does not approach a finite number. It's unbounded. So it goes on to infinity, it can go on to some non-finite number, which is usually going to be infinity. That means that we're multiplying it by 1 or greater each time. So all our numbers are getting progressively bigger. So obviously that sum is not going to reach a finite value. So that's really a brief summary of our geometric series and the specific conditions we have for a converging or diverging series. Now let's discuss our sum of an infinite geometric series. And I want to specify that this should be converging, because if this series converges, then only there can be a sum. So really, if I have a series from n equals 0 all the way to infinity of that a times r to the n, notice how it's the same. A is that first term, r is that common ratio, what we're multiplying each time, and n is just going to be that arbitrary variable we use. So if we have our series here where now, because this converges, again, that same condition here, the absolute value of that common ratio has to be between 0 and 1, non-inclusive. Then this sum is going to be a, so that first term divided by 1 minus our r. So 1 minus our common ratio. So it's just our first term divided by 1 minus our common ratio. And this is a pretty straightforward formula. All you have to do is find your first term, and notice how that depends on what your n is. If your n is 0, well, your first term is a times r to the 0. If your n is 1, well, then you're going to have to do some extra algebra here and find that a times r. So that's what you need, your first term and then your common ratio. And how do you find that? Well, sometimes our series can be in this summation notation form. Then it's really easy to identify which is which. But if it's not, then you just have to expand the series out and see what number each term is being multiplied by. And that's just going to be your common ratio. So now that we have that out of the way, let's go ahead and put these skills to use. Let's do some practice problems so we can really see what's going on here. Alright, so if they have given me a series from n equals 0 all the way to infinity, and they have this form written here. Now this might be a little bit different from what we have seen before, but it's really not that different. Because why? Well, we can rewrite this. We can rewrite this series from n equals 0 all the way to infinity, and if it's 5 in the numerator, that's the same thing as 5 times something else. 5 times 1 over 3 to the n. Alright, and I just expanded that out. And we can actually rewrite that once more. We have our first term 5 here, but our common ratio is a little bit hard to differentiate. So we can rewrite that from n equals 0 all the way to infinity of 5 times, since it's 1 over 3 to the n, that's 1 over 3 whole to the power of n, because 1 to any power is going to be equal to 1, and that 3 to the n, our denominator, stays the same. So that is ultimately how we are going to expand that out. And now really clearly, we can see which each of these components are. So 5, that's our first term. And notice how if we're starting at n equals 0, 5 is going to be that first term, because 5 times 1/3 to the 0, well, that's just 5 times 1. So 5 is that a. And now our 1/3, well, that's going to be our r, the common ratio. So what we multiply each term by. And if you want to expand the series out, we'll go ahead. So we're going to have 5 times, notice how that's first term, 5 times 1/3, so that's a plus, 5 times 1/3 to the first power, that's our n equals 1, plus 5 times 1/3 to the second power, n is 2 there, and then it goes on and on, plus all the way to 5 times 1/3 to the nth power. And notice how that's similar to what we were given here. Alright, so what do we know about this series? Well, we know our ratio of r, which is the absolute value of 1/3, which is equal to 1/3. Well, since that is less than 1, we know that this series converges. It reaches a finite value because each time we are multiplying by a number that is small enough where our sum of this series can actually reach a finite value. So we know that this series converges. All right, so if we know the series converges, why don't we find what it converges to? And what is that called? That is called our sum. That sum of that infinite geometric series. And how do we find that sum? Well, just use the formula we have up above here. So that sum all the way from n equals 0 all the way to infinity of the 5 times 1/3 to the n. Notice how we just rewrote that. This is equal to this. So they're both equal. We just expanded it out to the different sets of parentheses. And so we can really see our a and common ratio and n here. So we just wrote in this form. So the sum of this, that's going to be, let's just follow the formula here. A first term. Oh, look, we already have that here. This is going to be the 5. That's going to be our first term. So 5 divided by 1 minus r is going to be our common ratio. So what are we multiplying each term by to get the next term? Well, that's going to be 1/3. 1/3 is our common ratio. And it helps if you write these components out before you start solving for the sum. So you can say here your a1 is going to be that 5 and your r is going to be that 1/3. Now all you have to do is just plug and chug into the formula and it gets really easy. So 5 is our a1, 1/3 is that ratio. All you have to do is simplify this. So 5 divided by, well, 1 minus 1/3, that's 3/3 minus 1/3, which is 2/3. And then if I do that, it's 5 times 3 over 2, because I just rewrote that and took the reciprocal. And that's just going to be our 15 over 2. So that final sum of that geometric infinite series is going to be 15 over 2. And you can rewrite this as a whole, as a mixed fraction if you want, or leave it as an improper. They're all equal. So this can also be rewritten as 7.5. So really, it's pretty interesting to see how even though this geometric series goes on to infinity, notice that upper bound is infinity here, we were still able to find a finite sum. So this series eventually reached a finite value of 15 over 2, and we found that. And how do we know that it reaches a finite sum? Well, because that ratio, that common ratio of 1/3 was less than 1, because we were multiplying each term by something so small that the end result could be an actual value that we were able to calculate. So that is something that is pretty interesting about geometric series. As you can see here, we have all the detailed formulas and each component of the formula here, and we were just able to use that to our knowledge to apply it to a specific geometric series here. Notice how it converges and find that finite sum. So that is pretty much it for this lesson today. If you guys found this useful, please give it a thumbs up and share this to those who may need it. And if you guys have any questions, please feel free to write them down in the comments below, and I'll get back to you as soon as possible. That's pretty much it for geometric series, and we'll see you next time. Bye!